term. The second thing about, before we get started today, is your first Cengage assignment. It's due this Sunday, all right? So if you haven't worked on it yet, you have a little bit of time, but do not wait until the last minute. You won't be able to finish it. As I told everybody, the average time for my student to finish their Cengage assignment is about 8 hours for this first one. So I warn everybody, like, start early and try work on whatever you can, but don't wait until the last minute. Like, please, please don't wait until the last minute. It's not good for you, it's not good for me. And the other thing about the Cengage assignment, you'll see there are problems with 0 point. So those problems are for practice only. Like, you don't need to work on it. But if you're interested, you're free to practice over those 0 point questions, like three-dimensional parking in the box. We didn't cover it in class. I'm not going to test you on those topics, but you're free to play around with those problems. All right, whenever you see a 0 point problem on Cengage, that's not being graded. It's not going to affect your grading anyway. All right. Do you have any? Yes.
Will the Cengage assignments be available after the deadline?
I think so. Right now, my setup is after the deadline. You can still go back and use it as a practice. I need to double check on my setup, but if you can't access it after the deadline, let me know and I can work on it. Yes. Well, you need to finish it by Sunday night. No. Yes. You can answer it on your iPad. I think I write it down there. If not, but you can use whatever you like. Right? You can use lecture note, lecture recording, textbook, equation sheet. As long as you don't talk to each other, you don't search on the internet, that's not very, those two are prohibited. But everything else, whatever we use in class, you can use it on the exam. Yes? I can't tell if it's shorter or longer. It's just a different chapter. All right. Yes. Sorry, I don't understand your question. Yeah, I just answered that. You can use your iPad to answer your midterm. And download it as a PDF, you upload it as a PDF. All right, so we'll get more into the midterm. Your TA will post review sessions sometime soon. But that's all for our arrangement for now. We'll have more details coming up. And we are, again, remind you, the Cengage assignment is due Sunday. Don't wait until the last minute, not good for you, all right? Okay, and now we're moving on to chapter 5. So far, we covered a lot of basic quantum mechanics, and some of you might be asking the question, so how is it related to chemistry? But after all, the title of this course reads chemical structures. So one of the fundamental questions we're trying to answer is what is an atom? So for these two lectures, we'll spend some time just talking about the very, very basic atom, which is hydrogen atom. So hydrogen atom only have one electron. So it's it's the only atom, technically speaking, we can solve for its own Schrodinger equation. We know everything about it. So today we'll be talking about 3 different topics. The first one is a brief introduction to spherical coordination system, not any details, but as long as you know what that means. Second one, we'll talk about the Schrodinger equation for hydrogen atom. And we're going to be focusing more on the physical meaning of the Schrodinger equation for the hydrogen atom, and also what does a wave function mean when we're talking about the hydrogen atom. And the very end, we'll be looking at s orbitals of the hydrogen atom. Okay, so a quick review for our Wednesday lecture where we talk about the Schrodinger equation. Right, so what we have, Schrodinger equation is a differential equation. You have the Hamiltonian acting on the wave function, and the solution of that differential equation gives you the wave function that tells you everything. For example, including like energy levels of that particle. Right. And the other way to use the Schrodinger equation is to help you finding the probability of knowing where that particle is. So the way to do it is by setting up the integration on the phi x squared dx. I think I have that wrong. I need to correct that in our blank note. Okay, so that's a review. That's what we discussed about Schrodinger equation. The first thing first, for the one-dimensional particle in a box, we talked about it in the Cartesian coordinate, just one-dimensional x, y, and z. It's easy to understand. But if you think about it, there is an obvious problem when we're trying to use the Cartesian coordinate to describe an atom, where we know there's a nuclei in the center and an electron that's somewhere in space. Right? So the distance between that nuclei and the electron is more or less a spherical interaction. Or if you think about Coulomb's law, it depends on the distance between the electron and the nuclei. So if we want to use the original Cartesian coordinates, say here is our P1 of interest at position x, y, and z from the origin 0, 0, 0. And in order to find this distance here, this r equals to a quite complicated representation of square root of x squared plus y squared plus z squared. And that's not ideal. We don't want to deal with this complicated mathematical representation all the time. So that's why from today, when we're talking about the hydrogen atom, we'll be using the spherical coordinates, where the position here, this position P, instead of using x, y, and z, is defined by r, which is the distance between that position P to the origin, and then two angles, theta and phi. So this one, r just equals to the small r. They're working the same way. I mean, the only difference is now we use different variables to define the point in space. And since now we're looking at this three-dimensional problem, naturally we'll be facing problems like partial derivative and also like integration is three-dimensional. But again, none of these mathematical details will be tested, but it will help you to understand it. So that's a very, very basic of spherical coordinate. Just we're gonna use r, theta, and phi. And r, theta, and phi are just variables we use to define the position of that particle in the three-dimensional space when we're talking about the hydrogen atom. Okay. All right. So moving on. Again, let's just take a quick step back and just think about our one-dimensional time-independent Schrodinger equation for the particle in the box, right? So this is what we did on Wednesday, which this first part is our kinetic term. And then the second part is our potential term. And if you remember, yesterday we solved our Schrodinger equation, and we only have one quantum number, which is talking about that energy levels, right? So in this case, in this one-dimensional problem, we have one quantum number. Right, so the take-home message here is we're talking about these energy levels, n equals to 1, n equals to 2, n equals to 3. So somebody asked me what that n means. So that n is a quantum number, where in this case, in the one-dimensional problem, we only have one quantum number. So that's what that means. It's for those energy levels, right, those n equals to 1, 2, 3, those are our quantum numbers. We use quantum number to designate what's my energy level. It's ground state, first excited state, or so on. So that's for the one-dimensional particle in a box. 1D problem have one quantum number. But when we're moving to the hydrogen atom, which is in three-dimensional, now we have a more complicated system, where in this case, let me put the energy on the left here, just to keep it consistent. Energy on my wave function, which is a function of r, theta, and phi. And now it is a three-dimensional problem, so we'll have at least three quantum numbers to describe this wave function, n, l, and m. Similarly, we have a Hamiltonian acting on this wave function, n, l, and m, as a function of r, theta, and phi. So here what we're meaning is each combination of the quantum number n, l, and m. We'll see the meaning of these quantum number very soon. So each combination gives you a specific wave function that's corresponding to that specific quantum state. All right, so the combination of the n, l, and m give you a unique quantum state. And for that unique quantum state, you have a wave function associated with it. So a little bit of the extra, so that Hamiltonian here, you can also write it as a kinetic term, which is negative h bar squared qm, and Laplacian, which is this, also a differential equation, minus the potential term, ke squared over r, so that's just your Coulomb's potential. But if you're really interested, you can take a look at the Laplacian differential equation and see if you can solve it. I'm not going to ask you to solve it. I just want to show it to you. Okay. So in this case, the more important thing here is now we have three quantum numbers describing one wave function. So what it comes from is coming from solving the boundary conditions. Again, this is a review. Remember, we use these boundary conditions to solve the Schrodinger equation. And applying these boundary conditions, we can get three different quantized properties corresponding to these three quantum numbers we talked about. So in this case, we have the quantum energy, which is E. The square magnitude of angular momentum is also quantized, the L square. And then the projection of the angular momentum on the z-axis is also quantized. So we have three different quantized values by solving the Schrodinger equation for the hydrogen atom. So again, what we mean is we have three different quantum numbers to describe a specific wave function and the quantized properties associated with it. All right, so each combination of n, l, and m give you a specific quantum state and a specific wave function. So this is what we mean here by saying each set of the quantum number identifies a specific quantum state. We'll see some example later on, but before we do that, I want to go into a little bit detail in what these quantum numbers mean and how do they actually relate to the physical properties we mentioned. Let's look at the first one. So the first one is what we call the principal quantum number, n, which corresponds to quantized energy levels. So if you draw it out, remember in the Bohr model, you can have the n equals to 1, 2, 3. Etc. So for hydrogen atom, we have z equals to 1, or sometimes we keep the z around just for one electron system. So the energy level is going to be the same as you solved in the Bohr model, which we have En equals to negative E squared ME, well, E force ME, 8 epsilon naught squared, H squared, Z squared over N squared. So this is exactly what we have in the Bohr model, because the Bohr model is doing a very good job solving for the one electron system. Our hydrogen atom is a one electron system. So these two energy equations are actually identical. And this first part is just our Rydberg. And then n equals to integer numbers. All right, so this n is our principal quantum number. It's corresponding to the energy levels. But we have two more quantum numbers that we need to describe any specific quantum state. The second quantum number that we're interested in is called the angular momentum quantum number, or we have a small l. So for the angular momentum quantum number, we have the angular momentum squared equals to L times L plus 1 h squared over 4 pi squared. So that's how you use the quantum number to get the physical property, which in this case is angular momentum squared. One important thing to keep in mind is the selection rule. So the L, remember when we were talking about the principal quantum number, it can be any positive integer number, right? 1, 2, 3, all the way to infinity. But for L, it has some limitation. So L can start with a value of 0, 1, 2, all the way to n minus 1. So this is a point that I want to stop a little bit, because if you're thinking about a quantum state, it has 3 different quantum numbers. So if my n equals to 1, L can only take one value, which is 0. Right? So the maximum the L value can be is n minus 1. So take a minute and think about it. If my quantum state now have n equals to 2, how many values my L can take? 2 values, actually, 0 and 1. Right? So the maximum there is 1, minus 1. So if my n equals to 3, my L can be 0, 1, and 2. So it just depends on what the value of n is. Your L has certain limitations there. So conventionally, we call these L orbitals with different names. So if L equals to 0, that's an S. If L equals to 1, we call it a P. And L equals to 2, that's a D. And L equals to 3, that's F, and so on. So one of the things now to think about it is we have 1s, 2s, 2p, and so on. Have you ever thought about why it doesn't exist a 1p atomic orbital or 1p combination? So imagine a 1p combination, what does that mean? So 1p means your n equals to 1, and L also equals to 1. So this disobeys the selection rule that's listed here. So that is why there doesn't exist anything like 1p atomic orbital or 2d atomic orbital. Just by definition, they do not exist. We'll see some more examples there, but let's move on to look at the third quantum number, which is the magnetic quantum number, abbreviated in M. So this is the Z projection of the angular momentum, Lz, which is m times h over 2 pi. And just know this is actually Bohr's postulate. And that's how Bohr actually got it right without knowing the full picture of the Schrödinger equation. But because his postulate is actually inherently correct, he's able to get the energy level correct using the Bohr model. And in this case, M also has certain selectivity rule. It can only be negative L plus 1, etc., 0, L minus 1, and all the way to L. All right, so for 3 quantum number, for my principal quantum number that's corresponding to energy, can take any positive integer number. My angular momentum quantum number L can take any value from 0 to n minus 1. The magnetic quantum number M can take value from negative L plus 1, all the way to L. So these are what we call selection rules, and let's see some examples. I know it's not very, it might not be working very well for you right now. So this is one of the example questions that I hope you can take a pen and paper out, and let's just work on it very slowly together, because you really need this information. So can you write all the possible quantum number combinations and their conventional name for n equals to 3? So remember, when we say conventional name, we say L equals to 0, that's S. L equals to 1, that's P. All right, so write all possible quantum number combinations for n equals to 3. So the only information we're using here is n equals to 3. So what we know is n equals to 3, and we can write down the allowed value for the other two quantum number. So the allowed value of L equals to 0, 1, and 2. And we need to stop here because we already reached the n minus 1, which is the biggest number your L can take. At the same time, we have the allowed value of M. And that's starting from negative L, which is negative 2, negative 1, 0, 1, 2. But it depends on what your L is. I normally write it from just like s orbital. So n equals to 3. So we're looking at 3s orbital. We'll talk about orbital very soon. But in this case, 3s orbital or 3s combination, we have L equals to 1, or the combination we're talking about is 3, 0, 0. All right, so this 3 is n equals to 3, L equals to 0, and then M equals to 0. That's the only possible 3s orbital you can take. Because for L equals to 0, your M can only take one value, which is 0. With me so far? Yes. Sorry, what's the question? So 3s orbital L equals to 1, because we're talking about the conventional name of these orbitals. L equals to 0 is equivalent to say that is an s orbital. Likewise, we also have p orbitals. We have 3p, or if we put it like this, sp, d. We have 3p, where, sorry, oh, you mean here this is 0, I'm sorry. I'm so sorry, yeah, that's my bad. L equals to 1. And for L equals to 1, you have 3 possible values here. 3, 1, negative 1, 3, 1, 0, and then 3, 1, 1. So my n, the principal quantum number, always equals to 3. And for p orbitals, my L always equals to 1. And my M can take 3 different values, so that's why you have 3 different combinations for your p orbital. And then the last one, we have 3d orbitals, where L equals to 2. And this should be easy, because we're just thinking about 3, 2, negative 2, 3, 2, negative 1, right? So my n and L stays the same. 3, 2, 0, 3, 2, 1, 3, 2, 2. So a total of 5 d orbitals available. So that's just using combination of different quantum number and also the selection rules. Do we have any questions before we move on? Okay, sounds good. And now we're moving on to actually see some of the solved wave function for the atomic orbitals of the hydrogen atom. So we'll start from the very simple one, which are s orbitals, or L equals to 0. So for each of the quantum states, N, L, and M, so each quantum state, N, L, and M, defines a specific wave function or a specific quantum state. And for each of the states, you can solve for a wave function, which is a function of r, theta, and phi. So the solved wave function of my s orbital will have two different parts. The first one is called radial part, as a function of r, and an angular part, which is a function of theta and phi. And I keep talking about atomic orbital, and I'll take some time to just really, really write it down. When we're talking about atomic orbital, what are these orbitals? They're just exact one electron wave functions. And we call them atomic orbitals. All right, so one of the common misconceptions is atomic orbitals are not electron moving trajectories. They are just our wave function. They describe the probability of finding the electron in certain space. So if you imagine how do we do it, that's just taking the integral of that probability density function in a given space. All right, so atomic orbitals are just one electron wave function that can be solved with an analytical solution. So atomic orbital and wave function, they're equivalent to each other. When we're talking about atomic orbitals, we're talking about the solved wave function of that specific electron in that specific quantum state. All right. And for our hydrogen atom, for our s orbitals, one quick question here is, again, pause a little bit and think about what is the quantum number combination for the 1s atomic orbitals. We just did it. I'm just going to do it again. So 1s atomic orbital means that my n equals to 1. That's coming from this principal quantum number. L equals to 0, for my s orbital. And also the only allowed value for n is 0. So when we're saying 1s atomic orbital, it's essentially saying it is equivalent to say, now we have a wave function in its 1, 0, 0 state, which is still a function of r, theta, and phi. All right, so make that connection. Atomic orbital and wave function of a given quantum state, these two are equivalent to each other. Okay, so before we move on to look at the actual wave function, do we have any questions on the conceptual parts? Okay, sounds good. So now we can look at the actual solved wave function for our atomic orbitals. So these are, you get it by solving the differential equation, by solving the Schrodinger equation. The mathematics behind it is actually quite complicated. You'll see it again if you're taking physics or physical chemistry for long enough. But for this class, I'm just going to give you the solved wave function, and we're going to use the solved wave function to get chemical properties of the hydrogen atom. So this is what we have. for the s atomic orbitals, where the angular momentum quantum number L equals to 0, it has no angular part. It means that our wave function don't have a dependency on either theta or phi. And that's why our s orbital is actually a spherical shape, right? It doesn't matter which angle we're talking about. So in this solved wave function here, this first part is our radial part. And in the theta, sigma, we have the r buried in there. So it's a function of the atomic radii r, or the distance between the electron and the nuclei. And then the angular part is just a constant. It actually is already simplified a little bit. So this A naught term, that's our Bohr radii, actually has more constant buried in there. All right. So what does our wave function look like? So if you think about it, these parts are just constant. This is just constant. What we essentially have is just plotting against this exponential term here, right? So a typical plot of this exponential of e to the negative r with lots of constant. It's more or less a negative exponential function. So it's all the way going down, has 0 nodes. That's typically what it looks like. The next one is how are we going to use the solved wave function to get properties out of it? The most obvious application of our wave function is to answer the question, where is my electron? Where is my electron in the hydrogen atom? So you can imagine that we have lots of calculus coming up, but again, try to bear with me, don't be frightened by this equation. The first thing we can use our wave function is to solve for the probability of finding the electron somewhere in space. So here we're talking about the total probability. So it's a triple integral because it's a three-dimensional problem of r, theta, and phi. Even if your function doesn't have a dependency in theta and phi, you need to take that theta and phi into the integration calculation. I'm going to skip my derivation here. If you're happy with calculus, do it yourself. So the result here is to get the probability of, is in order to solve for the probability of finding the electron somewhere in space between 0 to r, we can get an integration to do that. It's what we do. Let's do an example together. What is the probability of finding a 1s electron in a sphere of r equals to 2a naught? So in this case, let's solve it for both hydrogen and helium plus. And I mean, we'll see like how it turns out. But if you have z equals to 1, that's p equals to, let me copy that down here. So here, this one is our general formula. And we can plug in the numbers. So for z equals to 1, we have p equals to 4 a naught third from 0 to 2a naught exponential negative 2r over a naught r squared dr. And then for z equals to 2, for helium, we have p equals to a much larger number. Let's see, a naught 4 times 2 to the third, 2a naught from 0 exponential negative 2r over a naught r squared dr. So there are lots of things we can do, but just to take a quick look at it, we know that this P hydrogen and the P helium, you can compare them, and we know this is going to be a much larger number, just because there's the square term, this third term in front of it. So you can do the integration, or you can do the integral yourself. It's also in the annotated note. But let's assume we did it with magic calculus. And the first one is going to give you a result of about 76.2%. And the bottom is going to give you a result of about 98.6%. All right, so what we're getting is the probability of finding a H atom or helium plus electron in a sphere with R equals to 2A naught. So we're just calculating the probability of finding this electron somewhere in space for this entire sphere with radius equals to 2A naught. So the other way, if you go back to this graphical representation, look at this graph here. What we're getting is the total probability of finding this electron in this sphere, this entire sphere, with R equals to 2A naught. So it's the entire sphere we're talking about right now. So this involves some calculus, and if I'm gonna ever ask you a question on it, I'll provide you answer to those integrals. But unfortunately, I don't have enough time in class to go over the derivation. But if you have done that in your calculus class and you want to play around with it, you can solve it and see how it turns out. The other one, that's probability. This one is a little bit different. This one, the textbook talk about it in more detail, but it's a slightly different probability called radial probability. So what it means is we're talking about now the probability of finding the electron somewhere within a thin sphere share of thickness dr located at distance r from the nuclei. So this one is different from what we talked about before. Before it's like the entire sphere. We're taking the integration of that entire 0 to 2 angstrom. So now if we're talking about the radial probability, again, this figure is a nice way to look at it, is we're just looking at this very thin sphere. As at position r, we have a dr. We have this little thin layer. It's still spherical. It's like a shell. It's like the eggshell, if you may. And what's the probability of finding the electron there? And the reason we introduce the radial probability is because it's a little bit easier to calculate. So for our spherical s orbitals, this radial probability is roughly equals to r squared times the radial part as a function of r squared and times the thickness dr. So see some of these practice problems in your Cengage assignment, and I hope this equation doesn't appear too foreign to you. Just a different way, different type of probability as we discussed before. Okay, and we have some more ways to use our solved wave function. We can also use our solved wave function to calculate the average value of the distance of the electron from the nuclei in that orbital. And that's what we're talking about, the average distance, or atomic radii, if you like. So in this case, we have this distance as a function of both the principal quantum number n and our angular momentum quantum number L. So the equation is given by n squared A naught divided by z. The larger the z, the smaller the average distance, which is also something we expect, right? So if the atom has more nuclear charge, the atom shape, the electron cloud will be smaller, more contracted to the nuclei. And then we have properties that's contributing from the L, which is your angular momentum quantum number. So we can do this calculation here together. Let's say, what is the average distance of a 1s electron in hydrogen and lithium 2+, and see how do they compare. So for hydrogen, we have V equals to 1, and 1s, n equals to 1, L equals to 0. So this R 1s for hydrogen equals to, so n equals to 1, z equals to 1, just A naught times 1 plus, this one is 0, so this entire term went away, 1/2. And the average distance for the 1s electron in hydrogen atom is about 1.5 angstrom. Bohr radii, sorry. Likewise, we can do the same calculation for lithium with V equals to 3, N equals to 1, L equals to 0. So this R1s for lithium 2+ equals to A naught divided by 3. This 3 comes from the Z here. Right. And times 1 plus 1/2 equals to 1/2 A naught. So it's also like intuitive to what we're thinking about, the atomic size. Right? If you have more positive charge in your nuclei, the electrons are more likely to locate closer to the nuclei because of the stronger Coulomb's attraction. So that's our 1s atomic orbital. So we discussed about lots of the things. Let me just go back and rewind a little bit. The first and foremost, the most important thing here, when we're talking about atomic orbital, they're the same of these one electron wave functions with specific quantum states. So what we're talking about here is for 1s atomic orbital, you can write out the quantum number combination here. So 1s is corresponding to a quantum state of 100, or your wave function in quantum state 100 is a function of r, theta, and phi. We looked at the general form of the 1s atomic orbital. So for each different atomic orbital, you should expect a different wave function. So this is only the wave function for the 1s atomic orbital. It's the 100 wave function for the 1s atomic orbital. And now we're moving on to look at the atomic orbital of the 2s wave function. All right, so 2s wave function, again, it's same to say 2s, that's 200, right? 2 represents that principal quantum number 2. L equals to 0 for an s orbital. And the only value your m can take is 0. So here we have 2s and 200. And here is a solved atomic wave function. And in this one, I want to specifically highlight this one term that writes in front of the exponential term. So what that means is if you plot out your wave function as a function of your radii, now you have a node. Remember when we were talking about nodes in your standing wave, node means your wave function is going to change phase, right? So what it means is if you plot it out, this is your phi 200 as a function of radii, now you have a node. That's where your wave function is 0. So we can calculate where that node is by looking at the wave function. So we have the node. At the node, we know the wave function equals to 0. So that's phi to x equals to 0 at the node. So what it means is 2 minus sigma equals to 0. And since we know sigma equals to ZR over A naught, Z equals to 1, we can solve for R. So 2 minus R over A naught equals to 0, and R equals to 2A0. So that's how you solve for the position of the node. And on the graph, we know that the position of the node is at r equals to 2A. The Bohr radii 2A here. What I mean by having a node in your wave function is if you think about the probability density function, right? So the probability density function P equals to 5 squared. And if you have a node at the specific position, you also have a 0 probability of finding the electron at that specific distance. So if you plot out the probability density function, what it means, there's 0 probability or a minimum of probability at r equals to 2A0. Or the other way to put it, so here's a real contour plot for the 1s atomic orbital of hydrogen atom. What we have is in the middle, when the distance is between 0 to 2A0, we have electron density. And when we're like beyond 2A0 to about 6A0, you still have some electron density. But in the middle, we have something called what we call a node plane. Means there is no probability or very low probability to find your electron somewhere around r equals to 2A0. All right. So how are we doing here? Okay. So, I mean, again, it has some mathematical background behind it, but for different atomic orbital for now, the most important take-home message is to make that link between atomic orbital and also your wave function that you solved. I left one more example here that's more calculation dense, saying you can calculate the radial probability to find the 2s lithium 3+ electron in that thin shell somewhere. So using that radial probability function, you can check these two radial probabilities you find and try to relate that with the node we talked about. All right, that's all. I'll be outside to take more questions if you have.